Ladies and gentlemen, welcome to math class, except for not really. We're going to do 13.1, which of course comes after 13.0, part 1. And that's going to be looking at 6 trig functions because why would we only use 3 if we can use 6? This starts with SOHCAHTOA, just like all things trigonometry. But what we're going to be looking at now is instead of just using sine, cosine, and tangent like we did in geometry and in 13.0, we're going to practice a little honors math and say, hey, what if we look at the relationships flipped over? What if we want to compare the hypotenuse over the opposite instead? So we're still going to have these relationships, but we'd be flipping each of these over. So for cosine, the hypotenuse will go over the adjacent. For tangent, the adjacent will go over the opposite. So they are reciprocals of what we used to use for sine, cosine, tangent. So if this is my angle, theta, the one that we always use, then across from that will be my opposite. And the hypotenuse has to be across from the 90, leaving this guy down here to be my adjacent. And while sine, as you know, goes opposite over hypotenuse, its reciprocal function is called the cosecant, and that flips it over. So it's the reciprocal of sine, but we usually think of it as hypotenuse over opposite. Let's see if we can zoom in a little bit. There you go. Cosine, as you know, compares adjacent over hypotenuse, but this secant flips the cosine over. So those are reciprocals, and so it therefore compares the hypotenuse over the adjacent. And tangent has a reciprocal function as well called, shockingly, the cotangent. And that takes your tangent, which is opposite over adjacent, flips it over to become adjacent over opposite. So we've been hiding these other 3 from you until Honors Algebra 2, so I'm sure this is a very exciting moment for you. I'll just let that sink in. Alrighty, so exact value, everybody's worst enemy, because what that means is that you can have no decimals, and as a result, you have to know a little something about rationalizing radicals and simplifying fractions and so on. So this is asking us to go ahead and find all 6 trig functions. What I usually do is find these 3, just kind of thinking back to what do I know about SOHCAHTOA, and then I just take each of them and I flip them over. And that will help me find my reciprocal functions with as little additional work as possible. So let's throw down our theta in this corner, making the 15, which is straight across from it, our opposite side. The 17 is across from the 90, making that the hypotenuse. And then that would make this one down here the adjacent side. And you'll notice that that side doesn't have a number. So we have to think back to stuff we already know, like the fact that a squared plus b squared equals c squared. So in this case, whatever this side is down here, squared plus 15 squared has to become 17 squared. And I find it impossible that that is news to you. So I would take 17 squared, and to get the a squared alone, I'd be subtracting the 15 squared. And so this one is actually pretty user-friendly because a squared is 64. So a is going to be a nice, pretty whole number. It's going to have a length of 8. So that will actually make our lives really easy. So now that I have my triangle labeled, I'll be able to buzz through these pretty quickly, just making sure that all my fractions are reduced. So when I go to do sine, I'm going to need the opposite over the hypotenuse, and so I'm using my 15 over 17, which doesn't reduce. And then to get the cosecant, I simply take the reciprocal of that, which is fancy words for flipping it over. All right. For cosine, I need my adjacent side, which is the 8, over the hypotenuse, which is the 17, which doesn't reduce. To get the secant, I simply flip that over, which also doesn't reduce. And you don't change it to a mixed number or anything. You just leave it as an improper fraction. Last but not least, we have tangent. Opposite is 15 over adjacent, which is 8. That doesn't reduce, and then I reciprocate to get my cotangent. So you're probably thinking this is the easiest thing in the whole entire world, which it is, but it can get messy, like this one. So here they're giving me information. I don't have a triangle. I always like to have a triangle to label and look at. It makes my life easier. I don't care if it's drawn to scale or anything. I just draw a right triangle. If this is theta, the cotangent, remember from up here, is the reciprocal of tangent. So instead of being opposite over adjacent, this 7 is adjacent over the 12, which must be opposite. So from my theta, the 12 is opposite, and the adjacent is the 7. So clearly my triangle is not drawn to scale, but nobody cares. But I don't know this. So I go back again to Pythagorean theorem and think 7 squared plus 12 squared, is going to be my c squared. So if I have 7 squared plus 12 squared, I have 193, which is not a pretty number, because if c squared is 193, then c is the square root of 193, which is unfortunate because that doesn't contain any perfect squares, and so that's just the number I'm going to have to use on my hypotenuse side. So that's going to make things a little bit messier. So opposite, adjacent, hypotenuse. So as I start to think about writing out my 6 trig functions, it's asking me to find the sine and the cosecant, so I actually don't have to find all 6. Yay. The sine of my angle is going to be my opposite over hypotenuse, and so in this problem, that's going to be a 12 over the square root of 193. But I can't leave that, so I'm going to need to rationalize that. However, since they want the cosecant, which is the flipped over version of that, I'm going to go ahead and do that before I rationalize. Otherwise, I'm going to have to rationalize again. Because when I flip this over as is, this is currently opposite over hypotenuse, and I want hypotenuse over opposite for the cosecant, then I'm going to go ahead and have the root 193 on the top, the 12 on the bottom, and I can just leave that. Even though it's like the world's messiest answer, it's at least rationalized and reduced, which it doesn't reduce, so I'm done. However, up here, I need to clean that up by getting rid of that square root on the bottom, rationalizing it. So I would have 12 square roots of 193 over 193. Now the concern would be, for simplifying, if the 12 over 193 reduces, I'd have to do that. So remember, on your calculator, you can do 12 over 193, go to math, and then the first function will change it into a fraction. Oops, sorry. It is a fraction, but if I hit enter twice, it shows me exactly what I started with, which tells me that it doesn't reduce, and I can just leave that answer as is. Then in this last example, we like to call the grand finale, I'm finding all 6 in exact form again. So do the same thing. Here's my theta, however, so pay attention to that. That means straight across would be the opposite side. Then across from the 90 is my hypotenuse. And the other guy, the leg that's touching the angle, would be the adjacent. So this is the one that I don't know. So I do know that x squared plus 12 squared has to equal my hypotenuse squared. So solving for x squared, I'll have to take 14 squared, subtract the 12 squared, leaving me with 52. So 52 is not as bad as 193, except that this one can simplify, because back in the good old days when we had actual school, we learned that you can split this into a perfect square and whatever else makes 52. So in this case, 4 times 13. The 4 comes out because this perfect square, the square root of 4 is 2, and the root 13 is stuck in there. So this is going to be the length of this side that we have to use when we set up our problem. So our adjacent is a 12, our hypotenuse is the 14, and our opposite is going to be 2 root 13, which can make simplifying just a little trickier. All right, so sine we know is opposite over hypotenuse. So I just look at my picture. I always recommend labeling it, because then I don't have to think anymore. I can just write it out. But here I'm going to have the opposite, which is 2 root 13, over the hypotenuse, which is 14. The 2 and the 4 are both on the outside, so they reduce like they would if they were just 2/14 to 1 over 7. So this is my sine. When I flip it over for cosecant, because remember that's how I get to these 6 reciprocal functions, I'm going to have 7 over the square root of 13, which I have to rationalize because math says so. So I end up with this, but 7 over 13 does not reduce, so I'm done. Cosine. I need adjacent over hypotenuse, so I go back to my picture. Adjacent is 12, hypotenuse is 14. And even though those are nice, pretty numbers, those reduce to 6 over 7, which makes an easy flip. 7 over 6. No rationalizing, no messiness. Favorite part of that problem. Last but not least, tangent, opposite over adjacent. So my opposite side is going to be the 12. No, that's a lie. The 2 root 13. And the adjacent side is going to be a 12. So these two are on the outside and can reduce to root 13 over 6. And then I will flip that over, giving me 6 over root 13. Not acceptable, so I go ahead and rationalize. I get 6 root 13 over 13. And again, this fraction part on the outside doesn't reduce. So when I'm done, I have my exact values, meaning no decimals, I've got radicals, I have everything reduced, rationalized, I'm good to go. So now I know everything about the 6 trig functions, and I can tackle whatever online learning resources you want to do to practice that. Good luck and peace out.